Swayam Prabha. Digital India. Educated India.
I'm going to continue talking about the Gibbs-Duhem equation, I think, for quite some time. Okay, I'm going to talk about we had two equations. I had mu1 minus mu1 pure So, binary systems, actually the equation itself I do not know if I wrote it in the final form. This is it, yeah, I wrote this. We rewrote this to get solutions of this form, where delta G is any function of composition such that, of course, f of 0 is equal to f of 1 equal to 0, because when x1 is 0 or x1 is 1, you have got the pure state, you do not have a mixing process at all. So, this is automatically a condition only. Now, we were discussing the van Laar equations or the van Laar theory. What van Laar said, we started with this. This is what I want, but this is what I can do. And luckily, thermodynamics tells me if I go around this way, I get the same answer if I do it this if I do it from A to B. So, this is pressure P, this is P equal to 0, T equal to constant. Then this is pure liquids, x1, x2, this is mixture, liquid mixture of composition x1, this is gas mixture of composition x1, this is pure gases. We made some assumptions, we talked about excess properties. So, you have delta G minus delta G ideal is equal to, is defined as G excess. And we said U excess is equal to, or the other way around, of this is set to 0, this is an assumption. I told you it is not a bad assumption in the case of molecules of similar size. This is also set to 0, this is generally a good assumption. When I say sound assumption, I mean you can verify using experimental data. that volume changes on mixing are generally very small. There is no ideal change in volume, there is no actual change in volume either. So, delta V minus delta V ideal is actually 0, both are 0. So, this is generally a very good assumption except in rare cases. In fact, you will be hard put to find counter examples where it is significant. There are some cases. This set to 0, I will say this is not in the same class as the thing, not bad for mixtures of similar molecular sizes. When I say similar, you can go up to 5 times roughly, it does not matter. One molecule can be 5 times as big as the other and still you will not have significant S, delta S, other than the ideal entropy change in mixing. So, having said that, he simply wanted to find U. So, he started with this equation du, you get du is equal to Cv dt plus he was calculating change in U at constant temperature in all the processes. So, to calculate delta U from one point to the other, he said delta U was simply integral of T dou P by dou T minus T dV from P is equal to P to P is equal to 0. This is delta U for AB. Now, this is where the boss stepped in, van der Waals. He said all fluids obey the van der Waals equation. The van der Waals equation is P plus A by V squared into V minus B is equal to RT. Because the physical arguments for van der Waals are very simple. Simply said there is a volume occupied by molecules B, PV is equal to RT was already known. He said the actual volume is the volume minus the volume occupied by the molecules, which is B, and that van der Waals already predicted that B would be of the order of the specific volume of the liquid, because after condensation it says that is the space occupied by the molecules and the balance space is available as for a ideal gas, because ideal gas consists of point particles plus free space, and this is not point particles. So, he said this is, he expected this to be of the order of V liquid, and generally densities of liquids are constant. So, when he said V liquid, he took it at the triple point, but he could have taken it almost at any condition. The argument here was that pressure is change of momentum, exchange of momentum with the walls, it is a rate of change of momentum. So, when a molecule collides and comes back, you take the change in momentum, divide by the time between collisions, and then you will get an estimate of the momentum exchange, you can get the pressure. This is in an ideal gas. In actual gas, he said that the forces are primarily attractive, the number of molecules striking the wall is proportional to the density, which is proportional to the 1 by the specific volume. The number of molecules pulling these molecules away from the wall and therefore reducing the momentum is also proportional to the number density, which is also proportional to 1 by V. So, effectively he said the effect of attractive forces between molecules is proportional to 1 by V squared. Depending on the molecule you have different A values, different strengths. So, he argued that A by V squared is the reduction in pressure caused by attractive forces. So, if we had treated the system as an ideal gas, the ideal gas would have actually exerted a pressure equal to P plus A by V squared, that is, this would have been absent in the ideal gas. So, this is effectively the ideal pressure, this is effectively the ideal volume, and PV is equal to RT. So, van der Waals said you have to use this equation, and this equation, because it has attractive forces, will predict for you condensation. It will actually do that. It can predict, you go on compressing the gas below its critical temperature, it will condense at some point. At some point thermodynamics will tell you what the chemical potential of the vapor is, chemical potential of the liquid is, and you can calculate this. In fact, one assignment I will give you is to prepare the van der Waals chart, the HP chart for a van der Waals fluid. If you do that once, then you know practically how the others are obtained. But let us look at this, because if I do not have these attractive forces, you can't produce condensation. So you will not get, when I do the chart here, you will get only this region for an ideal gas. There will be no condensation at all. If you want condensation, you have to introduce attractive forces. This V minus B will still will not give you condensation. In fact, P into V minus B equal to RT is sometimes called a hard sphere model. But let me get back here. I have got the van der Waals equation has to be used. So if I calculate P, so you get P is equal to RT by V minus A by V squared. So T dou P by dou T is simply RT by V. Which assumes that the A is an absolute constant, it is not a function of temperature. Improvements on the van der Waals fluid actually show that A is dependent on temperature, and therefore you have to use, it is rewritten in terms of another constant times a function of temperature. It is the Redlich-Kister equation. There is some slight changes, but there is a very successful equation of state called the Redlich-Kwong equation of state, not Redlich-Kister. In fact, when I went as graduate student to US, at that time Berkeley had Redlich teaching the course, teaching thermodynamics. Apparently it started with the Redlich-Kwong equation of state and ended with the Redlich-Kwong equation of state. He said there is no other fluid, so everything was done for the Redlich-Kwong equation of state. So you get this, so this difference is actually A by V squared. T d dou P by dou T minus P is actually plus A by V squared. So you get, this implies that delta U for a van der Waals fluid is actually A by V squared dV. So it will give you minus A by V. If I switch the thing, you get A by V at P is equal to 0, V is infinity. So you will simply get A by V. That is, I am writing this from P is equal to 0 to P with a minus sign. At P is equal to P, the volume is V, that is given by this equation. You have to solve the cubic and find the correct root, but A by V. So A has the interpretation of essentially the latent heat evaporation. Delta U is actually the internal energy change when this pure substance goes from liquid to vapor, right. So this is actually the, it is the enthalpy of vaporization is the latent heat, but enthalpy and internal energy change are approximately equal because P delta V is negligibly small. So this has an estimate of the latent heat. So A can be calculated as density times the latent heat. This V is V liquid, because you are talking of at pressure P you started with the liquid, and V liquid according to van der Waals is B, is the parameter B in his equations. So that is approximately equal to A by B. Should stay. So he has got delta U AB is equal to U excess AB, because delta U, if this was an ideal gas, delta U change is 0 because U is a function only of T, you are doing the whole process at constant temperature. So delta U AB is the same as U excess, because delta U AB minus delta U ideal would have been this, delta U ideal is 0. In fact for the whole process delta U ideal is 0. So this is equal to this, and it is equal to A by B. It is actually, it is not A by B exactly, it is x1 moles of 1 which you are evaporating separately. Per mole it is A11 by B, that equation is written per mole. So this is delta U is the specific internal energy change per mole of, for the pure substance I have to write x1 and x1 moles of 1, B1 is the parameter for pure 1, A11 is the parameter because it represents interaction between two molecules, you have to write 2 subscripts on it, plus of course x2 moles times A22 by B. And then delta U BC is equal to U excess BC, this is mixing of ideal gases. There is no change in energy when you mix ideal gases to form a mixture, there is no interaction energy to begin with, so there is no change in interaction energy. And then delta U CD is equal to U excess CD. Instead of this you are now doing condensation, so you will get a minus sign, right. The integral will go from P is equal to 0 to P is equal to P, so you will get a minus sign, you get minus A mix by B mix. So I have G excess for the process is equal to U excess for the process, this is AD. This is equal to U excess for AB plus U excess for BC plus U excess for CD. So you get G excess is equal to x1 A11 by B1 plus x2 A22 by B2 minus A mix by B mix. The concepts in this equation are basically valid, but this particular final result is restricted to the van der Waals fluid. So if you have a more complicated equation of state, you can use that and do the same calculations. Not many people have done that, and you can do that and get other expressions for G excess. Yeah. Because it represents attractive forces, and van der Waals recognize that if you mix there will be an A12. A11 is between 1 and 1, A22 is characteristic of the pure fluid 2, it represents interaction between two molecules. A12 is if you had one molecule and one 2 molecule, the interaction between them. Of course all these will be multiplied by Avogadro number because you are talking of per mole, whereas your interactions are actually between molecules.
And also when integrating to find delta U from A, B, we took it just, we ignored B from van der Waals equation, we took P as RT by V minus A by V square.
No, you can put RT by V minus B if I made that mistake. Even if you put V minus B, as long as B is constant and you differentiate with respect to T, it will disappear. If I wrote V, it is a mistake, it is V minus B. In fact, incidentally when I am on this topic, let me say this. So you get this is P is equal to RT by V minus B minus A by V square. So this is what he called P hard sphere, and then this is P or delta P due to attraction, due to attractive forces. That is what van der Waals argued. Much later, now we have an exact molecular theory of hard sphere fluids. You have a different expression for P hard sphere, which it is different from the van der Waals expression, and you can actually derive an exact theory for hard sphere fluids, and you can verify this because now you can do computer experiments, you can do Monte Carlo calculations. I will just describe that briefly because a very interesting set of calculations. On P hard sphere now we have an exact expression. So you can rewrite this equation as P hard sphere exact plus the same thing minus A by V squared. This equation has been, this is also, it is called Longe-Higgins Vidome equation of state after 3 people who wrote it down. They borrowed the P hard sphere exact from molecular theory. It has been fairly successful theory, that is van der Waals has many limitations. Qualitatively it is always right, but in terms of agreement with experiment has a large number of limitations. In the Longe-Higgins Vidome equation of state is much better than that. Means van der Waals was able to essentially quantify the effect of attractive forces quite well. The mistake he made was in the hard sphere estimate. Anyway, you can't call it a mistake. In 1870 that was well ahead of his times. So let me get back here. So what this tells you is that if you have an equation of state, you will anyway have to have parameters that are functions of composition, because when you write van der Waals equation, you write P is equal to RT by V minus B minus A by V squared. It is written for a homogeneous fluid. So A and B have to be functions of composition. So what van der Waals suggested, and when van der Waals suggests its law, at least at that time it was law, hard spheres. HS is hard spheres. If you take A mix, the probability of, in a mixture, the probability of finding a 1-1 pair is proportional to x1 squared. So you get x1 squared A11, probability of finding a 1-2 pair and a 2-1 pair, which are both characterized by an interaction 1-2, is 2x1 x2 plus x2 squared A22. So here he says assume that the mixture was a random mixture. Even to date molecular models only ask what is the departure from randomness. So you can get mixing rules that are slightly different from this. You must remember, although I called this a theory, basically you have 1 degree of freedom. There is going to be always guessing at one point. What he does is he uses the equation of state and finally gets it in terms of these, and you have to put in expressions for these. These are called mixing rules. Until date they are all empirical in classical thermodynamics. You simply put in a mixing rule, derive results, compare with the experiment. If it agrees, then you accept the mixing rule. There are hundreds of mixing rules. There is a whole paper on mixing rules in 1960s. I do not think a review has been written after that, because there are not many new mixing rules. I mean, you should realize that these coefficients are such that x1 squared plus 2x1 x2 plus x2 squared is 1. It is always true. All these equations will be of that form. Then there is one more, A12. See, I can get A11 and A22, B1 and B2 by fitting data for pure substances. That is, I take this equation of state. For pure one, I write P is equal to RT by V minus B1 minus A11 by V squared. Then I collect a lot of experimental data on PVT and fit the data to the curve. So I will get the best values of B1 and A11. One simple way of getting B1 is simply to take the density at the triple point. The triple point is invariant. So you can go to that triple point, measure the density of the liquid, and you will get the value of B. That is one way of doing it. Then you can fit A by V squared by taking the data. It is one parameter fit is trivial. So you get these. So I can get A11 and A22 from experiment. A12 is the hypothetical fluid in which all the interactions are of the form 1-2. That you can't get, because in any mixture you will have 1-1 interactions, 2-2 interactions and 1-2 interactions. I cannot isolate 1-2 alone. So this is invariably produced from experimental data on mixtures, knowing the pure parameters, pure substance parameters. The other way is to suggest what A12 would be. It has to be a mean between 1-1 and 2-2, and we are not very imaginative, we only know the arithmetic mean and the geometric mean. So you use one of them. Actually van der Waals suggested the geometric mean. if you like I will write this as k times in view of what has happened afterwards. This k12 is approximately 1, but if you put 0.98 and if you put 1, you will get a huge difference in calculated thermodynamic properties. So subsequently Prausnitz and co-workers have actually determined k12 for a very large number of mixtures. In some limiting cases where the forces, the dispersion forces are the dominant, there are many intermolecular forces, and even now our knowledge of intermolecular forces is not complete, but for pure dispersion forces you can show that this kind of result is exact. So it is exact in a certain limit, but as far as van der Waals was concerned, this combining rule was completely empirical. This is called combining rule. So one way of getting excess free energies is through the equation of state approach. This whole thing is called the equation of state approach, because you have a fluid described by an equation of state. The equation of state should describe both the gaseous state and the liquid state. Ideally that is true, we still do not have a single equation of state that correctly describes both the liquid and the vapor, but qualitatively the van der Waals fluid does. Many equations of state will predict the correct qualitative shape, but it is still difficult to get the exact thing. But every equation of state has parameters that are empirical, which are composition dependent according to what are called the mixing rules. These can be derived from theory to some extent in special cases, in other cases you have to approximate them. Right now we do not have a way of deriving this from theory. I mean we have a limiting cases where we can derive this from theory, but in all other cases we do not know the rules. So what we do is to use, usually the geometric approximation is used with a constant in front, empirical constant, you fit that to the data. But if I write this as A11 A22, then A mix is clearly equal to x1 if I put that in there, it is clearly x1 square root of A11 plus x2 square root of A22 whole square. So I can now write what Gxs is. This is x1 A11 by B1 minus suppose I need A mix, okay, I will just expand this. May as well get 1 by B1 x1 plus B2 x2 into B1 B2. This one will become this B1 suppose I should write B2. Let me see if I can get the algebra correct. Okay, this is B2 into B1 x1 plus B2 x2 into A11 into x1, that is one term, plus B1 into B1 x1 plus B2 x2 into A22 into x2 minus B1 B2 into x1 squared A11 So you can see the cancellations now. This B1 B2 x1 squared A11, this term will cancel with this term, and similarly this term B1 B2 x2, the second term will cancel with this term. what I have left is Gxs is equal to there is an x1 x2 here, x1 x2 here, x1 x2 everywhere. So, I will pull out the x1 x2. And A11 B2 squared plus A22 B1 squared minus 2 B1 B2 square root of A11 A22. So, this is what x1 x2 into square root of A11 B2 minus square root of A22 B1 the whole square. What I am going to do is multiply this by B1 B2 and divide by B1 B2. So, I already have a B1 B2 here. So, it will become B1 squared B2 squared. If I take it in here, it will become B1 B2 inside the square sign. So, this will become A11 by B1 minus A22 by B2 the whole square. And then of course, I have the B1 x1 plus B2 x2. This is the expression that Van Laar finally got. See, square root of A11 by B1 minus square root of A22 by B2 is a constant. So, what he is saying is Gxs is equal to x1 x2 by B1 x1 plus B2 x2. Or if you take Gxs by x1 x2 and take its reciprocal, this is linear in x1. So, if you plot, if you actually measure delta G and get Gxs, you have to subtract off delta G ideal and plot it against x1. If you get a straight line, then you know the Van Laar equation will fit this data very well. It was very important when I was a student, this straight line business. Now it is not. You guys use the computer, just hit the damn thing on the head, it will tell you whether it is a good fit or not, it will tell you what the standard deviation is. Earlier we used to do this visually, you have to go on plotting this data and show that it is a straight line. It still graphically is a good thing, but there are some significant things that Van der Waals said, and which is why Van Laar pointed out and became, therefore he was accepted very widely. I do not know, have you done principle of corresponding states? Have you shown these constants? You have done that a bit. So, you can show that the constant A is proportional to PC Vc squared, and B is proportional to Vc. So, this quantity A by B, square root of A by B is proportional to Pc. For a Van der Waals fluid is proportional to Pc. So, Van Laar said if the critical pressures are the same, the fluids will mix ideally because excess free energy will be 0. See, if A by B for 1 is equal to square root of A by B for 1 is equal to square root of A by B for 2, this will be true if critical pressures are equal. So, he said all fluids with approximately the same critical pressure will mix ideally, in the limited data they had at that time showed that that was in fact true. So it was hailed at that time as a very successful theory of liquids. So this is the final result in van Laar's theory, but nowadays we handle this much more easily. We don't go through equations of state, we don't go through mixing rules and combining rules. The equation of state approach still remains the same. This is the method. Everywhere you can change things. You can change the equation of state from van der Waals to any other complicated equation of state you like. You can take a more modern equation of state, substitute it there. You can change your mixing rules. Mixing rules simply have to show that in the limits they have to go to the pure component properties, but B can be written as any combination that goes to B1 in the limit as x1 goes to 1 and B2 as x1 goes to 0. Similarly for A, and then you have to assume a combining rule for A12. If you do all that, you will get a theory of mixtures, and people have done this repeatedly through this thing, and simply the ones that survive are the ones that agree with experimental data for a large number of systems. For each system you can't have a model. The easier way of doing the same thing is you recognize again mu1 minus mu1 pure is simply delta G plus x2 partial of delta G with respect to x1. So all I need is an expression for delta G. What Wohl said was, what can delta G be? In a binary system it has to be x1 x2 times some function of x1, and any function of x1 according to Weierstrass can be approximated by a polynomial. So he said just use a polynomial. For example, you write this as x1 x2 into a plus b x1 plus c x1 squared plus etc. If you want very accurate data, you have up to c x1 to the power n and so on. You go on increasing n. You want an accuracy, you have to arrive at in the scene at the right time when people already know the result but haven't stated it, then quickly state it, then your name is in the books everywhere. Wohl didn't do anything new, people had already been using the polynomial approximation. Simply wrote a paper, I don't know, 30s or 40s, I don't remember when. It is not an important paper, but somehow he managed to get credit for it. So everybody uses Wohl's expansions, and when too many terms are required, some wise fellow had the idea that instead of doing this, you make x1 x2 by, see this is delta G by x1 x2 is equal to f of x1. So if you write this as some other polynomial of x1, this is equal to a plus b, a prime if you like, plus b prime x1. In case this requires too many terms, the reciprocal hopefully will require fewer terms. Now this equation here having a not equal, all the others 0, a not equal to 0, I will take this 1, they have names because of people who derived various expressions earlier. A not equal to 0, that means all others are 0, it is called Porter's equations. You get the same equation when a prime is not equal to 0, except a prime will be 1 by a. Then if a and b are not equal to 0, you get what is called Margules, it is called the 2 suffix equation. It is called 2 suffix because Margules wrote it as a1 2, he wrote these with subscripts a1 a2 and so on. So it is called 2 suffix equation, all of these had 2 suffixes to them, it does not matter, it is when 2 are the thing, then you can similarly have a b c, a b c d etc. So you get various, all these are called Margules equations because he wrote them down. When a prime and b prime are not equal to 0, you get van Laar's equations. The structure is the same because if you look at van Laar's equations, x1 x2 by this is b1 x1 plus b2 x2. So in this case they are called van Laar's equations, this would be, now compare with van Laar, x1 x2 by g is, we will call this parameter alpha. Just call it alpha, if you like alpha 1 2. So you will get a prime plus b prime x1 is equal to b1 x1 plus b2 x2 by b1 b2 alpha 1 2. So what is this? Is b1 minus b2 into x1 plus b2. So your a prime is simply b2 by b1 or 1 by b1 alpha 1 2, and b prime is the coefficient of x1, except according to von Laar b1 b2 are actually volumes according to van der Waals, right. So they are known from pure component properties. So this b1 b2 all these are known, only constant that is unknown is alpha 1 2, whereas in practice people treat a prime b prime as independent parameters, and only if you treat it as independent parameters you get a good fit to the data. If you try to use the original van Laar equation with values for b1 b2 from experimental data, you do not get a good fit. This equation fitted all mixture data beautifully. Even now for alcohol water mixtures, it is probably one of the best correlating equations. This works very well, Porter's equations very well for like substitute. If you have A is equal to 0, this one works very well for simple mixtures where molecules are very similar. And then the second, this thing works a little better if the molecular separation is larger. A large number of studies earlier were funded by the petroleum industry, because they are the ones who had these various hydrocarbons coming out of the distillation column. They were similar, but they varied in molecular weight from very low to very high. You could go all the way from methane, molecular weight of what, about 15 16, all the way down to tar, which could be C56 if you like. You are talking of very huge molecular weight ranges, and if you have these mixtures you could describe them by various Margulis equations. Up to A, B, C not equal to 0 have been used quite widely. So this really is the summary. The way you do this is simply show that you can get from delta G, an arbitrary model for delta G, you get all the mu 1s. Once you show that, all you have to do is guess delta G. There is no restriction on delta G in thermodynamics, except that reasonable restrictions, like it has to go to 0 when you go to the pure state. It has to be a smooth function. You do not go on putting step functions and say delta G jumps here, jumps there. It does not do that in experiment. So you have to have a smooth function, that is all. And the easiest way to get a smooth function is get a polynomial or it is reciprocal. So you do that.